Roughly, a cosmic ray, a high-energy particle from outer space, passes through your computer. Actually, they pass through your computer every many per second, but about once a month it does enough damage to the state of the electrons in the computer that it flips one of the bits from 0 to 1. This isn't like an external environmental influence, and to correct for this, computer designers build in redundancy in the memory, so you can still recover the memory even if some of the bits have been damaged. It's a much more subtle process to do that for quantum memory, but that's the kind of thing we're working on here in the Yale Quantum Institute. So there's kind of a deep principle of physics that information is conserved. You can't create it. You can move information from one place to another, but it's a conserved quantity like energy or mass or momentum. When we encode information at the quantum level in the state of a few photons of light or in the state of some atoms, we would like that quantum state to be preserved over time. We know that, as people, that memories sometimes fail us, and when we try to build memory in a physical system, it sometimes fails us. So what does it mean that a quantum memory fails and loses memory? It means that the information you stored there went somewhere else. It's still in the universe, but it's left your memory. And in quantum mechanics, the way that happens is the external environment can learn the information. And if the environment has learned it, memory has partially lost it. What happens is that the memory becomes entangled with the rest of the universe.
There is this idea that everything has a physical storage in the universe, even memory, that I've been grateful to listen and to share along this time at the Yale Quantum Institute. I've listened to these teachings and visions, and I try to make them live in my language. Visions of a multi-layered reality, already strongly related to my research.
These are the fundamental states that we use, the quantum states of light, and we use them to store information. So we say it's a quantum jump, so the state of light jumps from one to the other instantaneously.
And the light is not a visible light, it's like a microwave light?
It's a microwave light, yeah. The quantum state of light is very fragile, and so even if you observe it or measure it, you will destroy the quantum superposition.
When the states are rarefied and when the memory gets lost, you have this movement like a vortex?
Yeah, absolutely. One of the effects in our system is known as Kerr. Suppose we start off with this ideal state. The Kerr effect is like a vortex, exactly as you were saying, is a vortex which distorts this state. And so, you can see that the ideal state slowly becomes distorted due to this Kerr effect.
It's a natural evolution, but then it moves back to a sort
of exactly.
order.
It is reversible.
And physically, how do you inform the light?
It's all electrical signals.
So the idea is to start from the pure state of light,
right,
and to develop a 3D model also in the space. As the colors increase their density, we're going to put some hanging pieces over there, as we discussed last time. So the second piece should be here and here, which is this area.
Okay.
I was considering to start from the center, and this could be the top
Right.
You can move them a little bit in the space.
Yeah, okay.
Or
You can tilt them or like put them at an angle maybe.
so we can put
Yeah.
maybe the blue down.
Exactly. What we're actually looking at is the wave. So it will go in a cycle and the memory disappears.
As far as we can tell, the quantum theory applies to all scales. It applies to single photons, single atoms, single electrons, and to people and skyscrapers and airplanes, right? But it's mostly invisible to us, although I think looking at different experiments with light that you can do. We see the visible world because we see light. It's a reflection of the wave-like nature of light, and light travels from the world to us. It's a little easier to get hints of the quantum world through the light itself, and there are quantum effects in the world around us.
It's a matter of probability.
Yes, that's right. The particle is somewhere, but we don't know exactly where. And yet when you measure where it is somewhere, definite, it's where you measured it. And the act of measuring it gave it a position. It did not have a position before you measured it.